Hi, and welcome to the next video in the series to better understand the atomic structure. Today we're going to look at something that developed recently after Planck's hypothesis on understanding blackbody radiation, and that is the photoelectric effect, which is really famous and can be attributed to Einstein. Now, to introduce what the effect is, well, the photoelectric effect actually was noticed way before Einstein by a bunch of scientists, Hertz, Leonard, Millikan, most notably. They noticed that when you have light, and you shine that light of a specific color on a metal, then the metal starts releasing electrons. So you shine light on a metal and the metal starts ejecting electrons. This is the photoelectric effect. And we're going to see that it doesn't necessarily have to be a metal. This was just what was observed. And this, in fact, can apply to any sort of atom. So the reason metals were first observed is because the electrons in a metal are loosely bound. And this is very evident when you think about how metals can conduct electricity. So if you have, let's say you have a piece of metal, imagine you have fixed electrons. And electric current is the flow of charge, and in this case electrons. So if these electrons are fixed, then if you try and push it, they're not going to flow very easily. However, if these electrons are free and they exist sort of like a fluid, then if you push it, it's going to move just like how water flows through a pipe. So in this way, we can understand how electrons are loosely bound in metals. And if they're loosely bound, they require less energy to exit the atom. Or lattice. So a lattice is a structure where you have a bunch of atoms placed at specific locations. So like a crystal, for example. Salt, sugar, etc. So because the electrons in metals are loosely bound, shining some sort of light, even visible light, like the light you see around you, red, blue, green, can be used to eject electrons from it. And that is why this effect was first observed in metals. Now, how this effect was observed, or how the experiment was conducted, is relatively straightforward. So, some guy took a tube, he put two metal plates, connected them with a wire, and used an ammeter. So an ammeter measures current. That's a cell, by the way. And right now, if you don't do anything, this space is vacuum. So the circuit is open, which means no current flows. And so the reading on the ammeter will be 0. But they started shining light on one plate, which we're going to call the emitter. Now this plate is going to start ejecting electrons according to the photoelectric effect, which we're going to see in greater detail. These electrons are going to go towards this plate, and then that's going to give you the current, and it's going to close the circuit. Now this experiment is very useful in measuring two things. One is how many electrons are ejected from this metal, and the second is how fast they go. Because if you think about it, this electron needs to go all the way from this plate to the other plate. And that might actually influence something. Now, they wanted to do these studies to understand what parameters actually influence the photoelectric effect. So if you have light, which we can think of as electromagnetic radiation, right? Treating it as a wave, we have wavelength as a property, or frequency. So this is a typical property. Now, light always travels in vacuum at a speed of 3 times 10 to the power 8. So this is not a parameter we can actually change unless we change the medium in there, which we're not going to do for now. And you can also control the intensity, which is basically the power, which is again energy per time, over an area. So if you have a lot of power focused in on a small area, lots of energy in a short time, then you have high intensity. Right, so they wanted to see what's going to happen if you change this parameter. So, for example, the color of light that you use and the intensity or the brightness. Intensity can be related to brightness. It's not exactly brightness, but the brightness of light that you can use and how that will change things. So, interestingly, what they observed is, firstly, you need a minimum sort of frequency. So if you start increasing frequency, so you start at low frequency, high frequency, no matter what the intensity is, you always have a minimum frequency at which electrons are ejected. And how do they check if they're ejected? By checking if the circuit over here has current. If this reads current, that means electrons are ejected. Now, we're soon going to see why this cell is there, apart from driving the circuit. The second thing they observed is that if you increase intensity, current increases, which is what you would expect because you're giving it more energy in a shorter amount of time. But they wanted to look into this a bit deeper because current can increase if you have more electrons, right? More electrons being ejected, but that doesn't necessarily telling you how fast they go. So to understand the kinetic energy, which is a measure, which is an energy of motion, of how fast the electron is going, to measure this, they put this system in a field. So they set up an electric field, in this case. So remember, a field, and especially an electric field, is something that can interact with these charged particles. So charges interact with electric fields. So in the presence of a field, just in the same way objects with mass interact with gravitational fields, charged particles interact with electric fields. And in that way, we also have an associated potential energy. So in the same way as if you lift a box up and leave it, it's going to fall. So that's a box of mass m. It's going to fall to the Earth. Earth has gravitational field, which we're going to represent using a bunch of lines. And this has mass, which allows it to interact with the gravitational field. And this height at which you place it gives it a potential. So in the same way, if you place a charge in an electric field, it's going to have a potential. So if you leave the charge, it's going to go down. Well, in analogy. But it's going to interact with the field, basically. So by setting up the potential on these plates, what they're essentially trying to do is they're trying to stop the electron from coming. So by increasing the potential between these plates, or by increasing the field and the direction of the field, they reach a value of potential where the electrons no longer reach this plate. So the electrons come out, they come close enough, but they never have enough energy to actually hit the plate, which means you won't see a current. And by recording that potential, you're actually measuring how fast they're going. Because if an electron's going fast enough, and if your potential is low, potential is the field that's stopping them, so the stopping force, if that's too low, then the electrons will just go right past. They will slow down a bit, but they eventually will reach the plate. And if they reach the plate, you'll record a current. So by slowly increasing the potential for a given color of light or frequency of light, they manage to find values where the electron reaches its maximum potential. The electron's kinetic energy, or the speed, is not enough for it to reach the other end. And you don't observe currents. So once they saw this sort of first minimum frequency, they identified what is known as stopping potential, because it stops the electrons, right? Which tells you about the kinetic energy of the electron. So by doing these experiments, what they essentially found was that the intensity of light, so we're going to call it incident radiation because it's more formal, on the metal plate only controls number of electrons that are ejected. More electrons, more current. That's how they figured that out. The frequency, however, corresponds to, firstly, whether an electron is ejected, because it needs to have a minimum value, and also the kinetic energy of the electron that's ejected. So higher frequency means the electrons that leave the metal travel faster. And they found this by increasing the field against these electrons to stop them where you don't see current, and as soon as you stop them, you take that value of the potential and you match that to the kinetic, which is something we can look into in further detail should it be necessary. So this equation tells you that some multiple of frequency, some constant, is equal to whether an electron is ejected, so the minimum energy of the ejected electron plus kinetic energy. So this minimum energy is called the work function, which depends on the metal, obviously. And this kinetic energy is, well, half times mass times velocity of the electron squared. Formal definition. So the energy you give it actually comes from h times frequency. And by increasing the intensity, you're ejecting more electrons. Now, this part here, where you're treating the energy of light in terms of a multiple of its frequency, wasn't known until then. This is what Einstein came up with by applying exactly what Planck did. So Planck's quantization of atomic vibrations. Remember how Planck said, to explain blackbody radiation, that the vibrational energies are discrete and not continuous? So by applying this to electromagnetic fields or radiation, so by applying it to light, he was able to come up with the same expression as Planck. Energy is equal to h times frequency of incident radiation. And if you think about what he's doing, he's essentially treating the field as a packet in terms of its frequency. And this is how the concept of the photon came about, by quantizing the electromagnetic field, so any sort of light, into small packets. And he stated that electromagnetic interactions occur through packets called photons. So that means that you cannot have half a packet or a quarter packet So if you give something energy, it doesn't go like that. Rather, it's not in terms of a wave where you can take a part of it, but it's not always in terms of a particle either, which we can see later on, but it's in a packet of energy, and the whole packet must be absorbed. So the electron is here. Let's call this a electron in metal, and this is the energy level associated to freedom. It's a free electron. It's a free electron, so you will need to give it some amount of energy for it to excite. And this gap here is given by the work function, which is given by the frequency of incident radiation. Or in this case, it's the photon. So only if the energy of one of these photons, which is given by h, which is Planck's constant, which we saw earlier, times frequency, that's the energy of a given photon, only if the electromagnetic radiation has that frequency and the photons of the electromagnetic radiation have this much energy, only then will this electron jump to the free state. Now, if you remember, we did something very similar for the atom itself, electronic transitions in an atom. We said in order for an electron to go from an inner shell to an outer shell, it must receive a photon which has that exact amount of energy. Now the question is, why, if you give this a higher energy photon, does it still get excited? And the extra energy it's not very well framed, go to the kinetic energy. So why does, in this case, if you give it a photon which has higher energy than this gap, a little more, for example, somewhere there, why does it still go up there and the extra energy over here goes to the kinetic energy? But in the case of the atom, we saw that if the energy is between two shells, if that's one shell and that's the other shell, and if you give it a photon of an energy here, the electron will never go to this state. It won't absorb that energy at all because it doesn't match that. So why does this happen in the case of the photoelectric effect? And this is something we're going to learn later on in quantum mechanics by solving Schrodinger's equation. And the treatment of electromagnetic radiation, which I'm going to show here, as a bunch of particles that are flowing rather than waves, called photons, led to what is known as wave-particle duality. And we're going to look at this further in the next video.